Today, we take it for granted. Deep neural networks. Yeah, sure, they work. A few decades ago, we were not so sure. The invention of the first neural networks promised machines that can see and even think. Those early promises were not fulfilled. In this video, we're going to look back at the first rise and fall of the neural network. But first, this video is brought to you by the Asianometry Patreon. Early access members get to see new videos first, and selected references for those videos. Please sign up. Early access really helps me a lot, and I appreciate every pledge. Thank you, and on with the show. In 1943, Warren McCullough and Walter Pitts published a paper about neuron networks. The two came from eclectic backgrounds. McCullough was a neuroscientist with a bent towards philosophy. He took this philosophical approach towards biological questions, pondering the logical foundations of knowledge. In the 1920s, he started asking if there was such a thing as a, quote, least psychic event, end quote, as in, like, as fundamental to psychology as how the atom is in physics. McCullough benefited from an era of growing knowledge of the brain's physical nature. Eventually, he settled upon the neuron and its binary action of firing or not firing as his answer. Later, McCullough partnered with a math prodigy named Walter Pitts, a young self-taught genius thinking about the same ideas. They decided to write them up. McCullough and Pitts were inspired by Turing's 1936 paper about logical machines. Turing had shown that we can implement any computable algorithm in a series of elementary steps, the Turing machine concept. McCullough and Pitts' 1943 paper argued that a network of neurons, with the neuron's fire-no-fire behavior as its elementary step, can also do the same thing, as in, they can perform logical operations like simple arithmetic, data management, and even apply logical rules. The McCullough-Pitts neuron itself was very simple. It summed up a number of inputs, each given a certain weight factor. If the result of the weighted sum was higher than a certain threshold value, it activates, sending out a 1. Otherwise, it sends out a 0, staying silent. This is very simple behavior, basically binary Boolean circuits. The authors never intended to create a complete replica of neuron behavior. I mean, we still don't have that today. It lacked much of what we know actual biological neurons can do. For instance, biological neural networks have transmission delays, do synchronized firings, and modulate their firing frequency. The McCullough-Pitts neurons did none of those. 6 years later, in 1949, a Canadian psychologist named Donald Hebb proposed a neuropsychological theory in his book The Organization of Behavior on how these networks learn. The basic idea was that when two neurons fire together repeatedly, they strengthen their connections. The stronger those connections are, the more quote-unquote weight they get. Hebb's theories are often summarized as cells that fire together wire together, though the phrase is a bit of a simplification. The work done by McCullough, Pitts, and Hebb moved people towards the idea that we can generate complex human behaviors using connected networks of mathematical neurons. This school soon received the name of connectionism, a term first proposed in the Organization of Behavior. The late 1940s and early 1950s were exciting times in computer history. New developments in both hardware and software pushed the limits of what computers were capable of. New computing paradigms, like that for the stored program computer EDVAC, produced in consultation with John von Neumann, became widely popular. New fields of study emerged to bring together man and machine. In 1955, a mathematics professor at Dartmouth and MIT graduate named John McCarthy wanted to do a summer workshop on thinking machines. In November 1955, McCarthy, Marvin Minsky, and the information theory pioneer Claude Shannon wrote a proposal to the Rockefeller Institute for funds to do the workshop in the summer of 1956. McCarthy chose to name the workshop's topic Artificial Intelligence. The proposal said the following: an attempt will be made to find how to make machines use language, form abstractions and concepts, solve kinds of problems now reserved for humans, and improve themselves. The workshop began in June 1956. It lasted through to August 1956 and was set up as a rolling workshop with contributors presenting a series of papers. Memorably, two programmers, Herbert Simon and Alan Newell, presented a program called the Logic Theorist. Logic Theorist was able to prove 38 theorems from a book called Principia Mathematica. Simon and Newell did not particularly feel warm to the Dartmouth group, and reflecting back on it, they were perhaps a bit too arrogant, but their work was certainly impactful. Simon, Newell, and their collaborator, Clifford Shaw, later worked on other groundbreaking AI programs like General Problem Solver. They presented a framework behind these AIs, the Physical Symbol System. It's a theory that human intelligence stems from the manipulation of physical symbols using a set of rules. Some of the most successful AIs of the first few decades, General Problem Solver, ELIZA, and so on, were built this way. Another presenter was Arthur Samuel from IBM. In 1952, he programmed an IBM 701 computer to play checkers using symbols and explicitly programmed heuristics, which is pretty impressive since this predated Fortran, and thus you had to write in machine assembly back then. Samuel's program was an example of symbolic AI, but there was a twist. In 1955, he programmed this checkers program to play against itself and edit its own heuristics accordingly to get better. He later published a paper about this, calling the technique machine learning. The term stuck. In 1948, Alan Turing wrote about using a digital computer to simulate entire networks of neurons and their connections. He felt that such a network could be trained to do any task a human can, so we might consider these writings as being the first of a connectionist flavor. But unfortunately, his work predated stored program computers capable of pulling it off, and so it passed by without much discussion. So we generally attribute the neural network as we know it today to a psychologist named Frank Rosenblatt. A high school classmate of Marvin Minsky's, Rosenblatt studied social psychology in undergraduate and then earned a PhD at Cornell. After that, he joined the Cornell Aeronautical Laboratory with sponsorship by the Office of Naval Research. The laboratory specialized in technology for military aircraft testing. There, he started studying the psychology and human judgments of a pilot landing a plane. The U.S. military got interested in this and granted him a little bit of funding to apply probability theory to human memory and perception. This study led him to what he called the perceptron. The perceptron began in 1957 as a statistical model inside an IBM 704 computer. The results were promising enough for Rosenblatt and his team to start building a hardware device. But in July 1958, before the machine was even done, he held a press conference and made several comments to hype up the perceptron's capabilities. The New York Times quoted him saying that the perceptron would be the first electronic device to think as the human brain would, that it could, quote, perceive, recognize, and identify its surroundings without human training or control, end quote. I note with amusement how, in the New York Times article, the Navy officers at the press conference said that they were hesitant to even call their perceptron a machine, more like, quote, a human being without life, end quote. Rosenblatt's Mark I perceptron machine, as it was called, was designed to identify divergent patterns. After being shown enough examples of these, it could grow to recognize them. This was done using a set of sensory units that either took in light or sound. This was called the sensory system, or S units. The sensory system units provide binary signals which were then fed into a single layer of McCullough-Pitts neurons. This was called the association system, or A units. The neurons inside the A units took a weighted sum of the inputs and checked them against the internal threshold, like as laid out by McCullough-Pitts. If it passed that threshold, the neurons would pass a signal to a layer of motor units, called a response system. This response is usually given as a series of lights, which the operators can review and correct as needed. Rosenblatt's primary contribution was a methodology of training this neuron network. At the beginning, all of the neurons' weights are set as random, like as how Rosenblatt believed a baby's weights would be. To train the machine, it would be shown a stimuli, like a picture of the letter X, and be allowed to respond to it via its R system. The onlookers then give feedback to the machine by adjusting the weights depending on whether the response was right or wrong. Rosenblatt argued that if the perceptron is capable of a particular classification task, then it can be taught that task using his training algorithm in a finite number of training cycles. Rosenblatt's work picked up followers. In the late 1950s, Rosenblatt visited the Stanford Research Institute, today SRI International, to preach the gospel. Two major individuals there, Bernard Widrow and his student Martian Ted Hoff, were convinced and created physical neural network devices of their own, Adeline and Madeline. But Rosenblatt's work had a far bigger impact on the greater public. He had articles in magazines like Science asking whether human brains were going to be replaced. Rosenblatt was a charismatic guy, and his rhetoric fanned the flames. He would say that the perceptron, quote, will be conscious of its own existence, end quote, or that, quote, we have a machine capable of having original ideas, end quote. Now, Rosenblatt and other people in the early neural network community readily acknowledged his machine's shortcomings. When the Perceptron Mark I was finished and shown to the world in 1960, he readily discussed its limitations. And as the years progressed, he began to more deeply regret the impact his words had on the field. His 1962 textbook, Principles of Neurodynamics, opened with an acknowledgement of the failings of that first 1958 introduction of the perceptron machine. He felt that it was a mistake that people saw the perceptron as a single machine that thinks, rather than a wide class of models taking after the central nervous system. All that being said, though, Rosenblatt's rhetoric irked a lot of people, particularly those in the symbolic AI community who felt that the work of the connectionists was not, quote, scientific, end quote. One of those individuals was the aforementioned Marvin Minsky. Early on, Minsky had done some work on neural nets, but left. Once at MIT, Minsky and his colleague Seymour Papert became leading advocates of the symbolic AI field. Throughout the 1960s, Minsky began arguing that there were seemingly insurmountable limitations to the perceptron. The reasons for this advocacy are multifaceted. There seemed to have been a personal slight over Rosenblatt's press, though it seems like Minsky and Rosenblatt were personally on good terms. But there was also a wider competition for research funding and researchers. Neural networks and other connectionism methods competed with their preferred method of AI, symbolic. And I should note that there are a few people who argue that Minsky and Papert's intentions were genuine. Indeed, the two said that they believed that tiny perceptrons were good for certain problems, tiny simple ones. But with harder problems, there were limitations that they did not see a way around. Minsky's and Papert's mathematical criticisms circulated throughout the community as drafts through the second half of the 1960s. What follows is an extreme simplification. At the heart of it, the criticism showed that there were limitations with single-layer perceptron models, the most famous of which was the XOR, or exclusive OR, problem. Single-layer perceptrons are good at classifying things that are linearly separable, like imagine some cats and Shibas on a table. If the cats and Shibas are arranged in such a way that you can separate them with a single line, then they are linearly separable. But for some other functions, this is not so easy. The XOR function is one of those. It takes in two binary features, 1 or 0, and outputs a binary, 1 or 0. The function returns 1 only if one and only one of the two inputs is 1. Otherwise, you return a 0. So 1 and 1, or 0 and 0, should both return a 0. 1 and 0, or 0 and 1, should give you a 1. You cannot draw a single linear line to cover all the correct inputs and outputs of the XOR function. The second major criticism that Minsky and Papert had of the neural network was how it grows in computational complexity. If the perceptron machine wanted to perceive a complicated connected image, like a letter or a group of letters, then it needs more units. Again, this is a limitation of the individual perceptron's simple binary outputs. And since this also means we need to retrain the neural network all over again, you can imagine this is like a programmer needing to rebuild their whole program from scratch whenever their problem gets a little bigger. It does not scale. As a final twist of the knife, or not, depending on your perspective, Minsky and Papert added that these problems were easily solvable with conventional symbolic algorithms in computers. In 1969, Minsky and Papert gathered their drafts, worked out the math, and published the book Perceptrons after a delay. There's a myth floating out there that this book ended the connectionism movement. Many neural networks investigators certainly felt so, saying that Minsky was on some sort of, quote, holy crusade, end quote. But what happened is a bit more nuanced. The criticisms of single-layer perceptrons were already long known and can be addressed with multi-layer perceptrons. The issue was that researchers didn't know how to train those deeper networks. Rosenblatt's perceptron learning algorithm, the one he used to train his first perceptron machine, only really worked on single-layer networks. That is because the weights going into each of the R system neurons are separate from each other, and we know the desired output. When you have more than one layer of perceptrons, we know the desired outcome for the final layer. But what about the middle one, the hidden layer, as it is so called? Rosenblatt and other people in the neural network community could not figure it out, perhaps due to a strong attachment to their single-layer training algorithm. In his experiments with two-layered perceptrons, he would randomize the first layer and freeze it, training the second as before. Between the known shortcomings of single-layer networks and the lack of progress in training multi-layer ones, momentum stalled, and the tides began to turn towards symbolic approaches to AI. The team at Stanford, once a leading hotbed of connectionism practice, turned to other things, and Ted Hoff left Widrow's team to work at Intel, where he came up with the ideas that led them to the first microprocessor. At around this time, Rosenblatt got really into studying the transfer of learned behaviors via chemical extracts. He began doing experiments where he trained naive flatworms to navigate a maze and then ground them up and fed their chemicals to new flatworms. He also got involved in the anti-war and anti-racist movements at Cornell, working with student activists to raise student representation at the universities and even tiptoeing into politics for the Democratic Party in 1968. But then in 1971, he died in a tragic boating accident at the young age of 43. 3 congressmen made a tribute to his memory, an indication of his influence at the time, and Minsky dedicated the Perceptron book in his memory. The loss of Rosenblatt solidified a general, broad redirection of funding, especially by the U.S. government, away from neural networks and towards symbolic methods of developing AI. Neural network research fell into a winter for another decade. If you're interested in a really deep and thorough but readable look into the perceptron controversy, as it came to be known, I suggest an essay of the same title by Yuxi Liu at Berkeley. Of course, we know what happens next. After many years, several neural network researchers added new complications to the perceptron to make it more useful, like a sigmoid output function rather than a binary 1 or 0, and then famously, a sophisticated algorithm emerged in the 1980s as a way to train multi-layer networks, backpropagation. Rosenblatt came up with that name too. He coined the term backpropagating error correction in 1962, but the algorithm it refers to today is way different from that. Despite all these discoveries, neural networks would still labor in the shadows for decades until the problems, the people, and most importantly, the hardware were ready. Alright everyone, that's it for tonight. Thanks for watching. Subscribe to the channel, sign up for the Patreon, and I'll see you guys next time.